Okay, good afternoon, everyone. Thank you for coming to another systems engineering seminar. My name is Andreas Malikopoulos. I'm with the CE department and also affiliated with the graduate field of systems engineering. Today is my distinct pleasure to have Professor Christos Cassandras from Boston University. Professor Cassandras is the distinguished professor in engineering at Boston University. He also the director of the Division of Systems Engineering, professor of electrical and computer engineering, and co-founder of the Center of Information and Engineering Systems. He received a bachelor's degree at Yale University, a master's degree at Stanford University, and a master's and PhD degrees from Harvard University. His area spans several areas, including discrete event systems, hybrid systems, cooperative control, stochastic control, with emphasis in applications related to sensor networks, manufacturing systems, and transportation systems. He has published more than 500 peer-reviewed papers and 7 books in this area. Professor Cassandras was the editor-in-chief in the flagship journal in controls, the IEEE Transaction Automatic Control, from 1998 to 2009. And now he's the editor in Automatica. He was also the president of the Control Systems Society in 2002.
12.
And
12.
12.
Don't make me older than I look.
12, yes, 12. He has been also a plenary keynote speaker in several conferences, including the 2001 American Control Conference, 2002 and 2016 Conference on Decision and Control, and 2017 IFAC Congress. He has received numerous awards. It will take a lot of time to go over the awards, but I'm going to just mention the 2011 IEEE Control System Technology Award and the Distinguished Member Award from the Control System Society. He's a fellow in IEEE and also a fellow of IFAC. With this, please join me in welcoming Professor Christos Cassandras.
Thank you very much. Thank you, Andrea. Pleasure to be here, and I'll get right to it. I want to talk to you about really bridging the gap between optimization and safety, roughly speaking. We all know how to optimize systems, but in certain systems, especially in today's world, we care a lot about safety. We care about guaranteeing safety, which is expressed through constraints in optimization. And that can be very hard if you want to solve a complete optimization problem, especially in real time, while guaranteeing that you satisfy all the constraints, which could be in the dozens. That's very hard to do in real time. So we have to find a way to bridge the gap between any old controller that might work but cannot provide guarantees, cannot provide safety guarantees or optimality, and the theoretical side, which is the optimization guarantees. And in particular, as I will explain, my motivation is autonomous vehicles in a transportation system. So, just to recap graphically, on the optimal control side, and I'm interested in dynamic optimization here, we know that we can solve optimal control problems. There's dynamic programming formulations, there's Hamiltonian formulations, calculus of variations, wonderful, elegant mathematical frameworks, but it's very, very hard to obtain solutions in reasonable time when the constraints become active. When the constraints are not active, unconstrained problems are relatively easy. It's extremely time-consuming to compute in general such solutions, and usually we restrict ourselves to simplified models. So at the end of the day, we have this question about, are we accurate enough? And typically, these solutions are not robust to disturbances. So on the other side, you can always come up with a good controller that works well. It's easy to obtain. You can handle nonlinearity and so on, but you cannot guarantee optimality. And generally, you cannot guarantee any constraints. So the goal, the general goal, is to bridge this gap and to find a framework which provides some sort of optimality, or can quantify the optimality, and definitely safety guarantees. And in fact, to some extent, safety may be more important than optimality in our case when we talk about autonomous vehicles, because I want to know that my self-driving car that I just bought for, probably a pretty expensive price is definitely safe. So, from a more practical standpoint, the motivation for this combination of optimality and safety is what we call the Internet of Cars. So, the message here is that with the emergence of all the self-driving cars, what we call connected autonomous vehicles, connectivity is part of the whole equation. We can create this environment with these wonderful calves that talk to each other and can also allow us to move from the selfish optimality of today's world, where we all drive very selfishly, to a social optimality, which is provided by automation. So I wanted to show you as an example of an environment in which you might want to test and experiment with your autonomous vehicles, this M-City testbed, which is at the University of Michigan. As far as I know, it's really the only reasonable size and reasonably practical environment in the United States to test your cars. And the reason I'm doing that is twofold. One, because actually Andreas and I had a grant in which we had our own autonomous vehicle, in which we played around in this environment for a few years and got some algorithms to work. And also because this is very useful to appreciate all the interesting conflict points where control and optimization play a role. So if I copy this picture, you see things like intersections with or without traffic signals, merging points, roundabouts. These are all great places where you have the opportunity to cooperate and therefore achieve better performance. Even on highways, you can create these areas wherever there's some kind of opportunity of merging and changing lanes to optimize the performance. So these we call control zones. And no matter what the control zone is, you want to formulate problems which, in a cooperative way, achieve desirable performance, measured as, number one, travel time through a control zone, for example, the time to merge, minimize energy through this control zone, maximize comfort, which can be quantified, for example, minimize jerk, and guarantee safety, very important. So, in the case of a merging problem, which is perhaps the easiest and used as a building block, you see that we can formulate a problem which pertains to this particular control zone. This is fairly arbitrary in terms of a zone within which there's enough communication or sensing for the vehicles which happen to be in it. We use some fairly simple dynamics to get the theory going. I show you what jerk might look like if you need to augment your model to capture jerk. And the goal is to control the acceleration of the vehicle in order to optimize our desired objectives and provide safety guarantees. So this is the problem that you can formulate. And it looks fairly straightforward because you have these two components, travel time and energy and comfort, if you so wish to deal with comfort. I already showed you the dynamics, and then there are speed and acceleration constraints, safety constraints, which have to do with not colliding with each other, and then there are some given conditions. And this can be done for any control zone. So the merging problem is kind of a building block. So if you want to solve this problem, mathematically now, the first question you might ask is it feasible? Because if you have a problem like that with lots of constraints, it might not be feasible. It's very typical. So you want to check that, and you want to check that fairly easily, because otherwise, what are you going to do? Every time a new car comes close, I have to recheck for feasibility before I even attempt to solve the problem. It makes no sense. Suppose it is feasible, then can we solve the problem without any constraints in real time to start someplace? If we can get ambitious and talk about solving it also under various constraints, but it might be nice to check, have easy checks, to see if any of the constraints really become active or not. Because if they don't become active, then I don't have to worry about it. If they become active, can I solve the problem? And what if, after you solve this problem and you're really happy, you find out that it takes, 5 minutes to calculate, what you should be doing over the next 300 meters or so? You can't do that. So this brings me to perhaps the most important part of what I want to tell you about, which is the planning versus executing issue of a trajectory. And this is where we get into the domain of what some of you may be familiar with, model predictive control. But I want to advocate for another new approach that has emerged, which employs control barrier functions. And I'll get to that, and I'll give you the pros and cons and what you can do. This is just a very brief and surely inadequate summary, but just to give you an idea of how people deal with these problems, you can have reservation schemes. So as you approach, let's say, a merging point, you solve a scheduling problem, essentially, which can be really hard, but it can be done. And then in the control and optimization context, you solve these problems either in centralized or decentralized ways. You can also have queuing modeling formulations, and so on and so forth. I will try to focus mostly on decentralized approaches for obvious reasons. I don't want to be driving a car where every time the car is supposed to do something smart, I have to rely on the link to some cloud, and then the cloud solving a problem and then getting bad my controls. Too many delays, too many opportunities for attacks, and so on. So let's take a quick look of merging as an optimal control problem. My point is that I can solve this problem analytically, completely, with some effort. This is a graphical depiction of the merging problem, just to give you an idea of there are cars from one road, cars from another road. They're all indexed in terms of their arrival times so that we can give them unique identities, and they all go through this merging point. The important thing to point out here is that there are some constraints, well, these are the dynamics, and there are some constraints that we're going to have to formulate, and the constraints are based on distances between cars. So this is, for example, the distance between any I and whatever the car ahead of it is, for example, 3 and 2. So that's the so-called rear end safety constraint, which can be formulated in this way. You want the distance to always be greater than something which depends on a fixed reasonable distance and the speed, because obviously, the faster you go, the more distance you should have to stop safely. And then at the merging point, you need a similar constraint so that the two merging vehicles, only those, and only at the time of merging, which is a decision variable, by the way, have to also satisfy this constraint. All right, so this is the problem. These are my objectives, time and energy, summarized here in this quadratic function. You can get into more complicated functions if you need to. We already talked about the dynamics. The speed and the acceleration constraints are bounds. That's normal. You have to put some order constraints to maintain the scheduling order. The schedule is typically first in, first out, but it doesn't have to be. You can create your own policy. And then I told you about the rear end and the safe merging constraints and some initial conditions. And that's the problem. And notice that it's decentralized because each one of these vehicles solves the problem by itself. It needs to communicate with at most two vehicles, namely the one in front of it and the one that it is supposed to conflict with at the merging point. So it's decentralized in the sense that it only needs some information from two vehicles. This is the unconstrained solution. It's actually pretty easy. It's a linear function for the control. It becomes quadratic and cubic in the velocity and acceleration and position. And this case applies to, you have to differentiate between these two different cases, whether the vehicle ahead of you is on the same lane or in a different lane. Sorry, let me see, 2 and 1, a different lane. Okay? So you need to separate these two cases, but the solution is there. You can get these nonlinear equations to solve, to get all of the parameters, these A, B, C's, and so on. You can do it. If you have constraints, you can still do it. This is just for the other case. But even if you have constraints, in which case you have to stitch together optimal trajectory arcs, and you have to also specify when does a constraint become active, when does it become inactive, if at all. It gets complicated, and you saw that I have several constraints. But you can still do that. So if, for example, this constraint becomes active, the rear end safety constraint, my control changes from simply linear to something which is nonlinear and more parameters to calculate. We can still do it. And this is just to show you exactly how you can calculate all of these coefficients. And the bottom line is we can even determine if there is an exit point from that arc or not. There's some conditions. This is the bottom line. We can always solve this problem, but from my experiences, when the problem is unconstrained, no problem. You can do that in much less than a second. But the minute that the constraints become active, and there can be many of them, it could take as much as 30 seconds to solve the problem in MATLAB. Okay, maybe we can cut that down to 3 seconds. Still too much. And to give you an understanding of how complicated things can get, these are trajectories of the optimal acceleration as a function of time for different calves entering the zone. So for the first one, it's no problem, because it's unconstrained. There's nothing to constrain it. So it's a simple linear function of time. But now let's look, let's say, at calf 3. And here you see that the optimal trajectory consists of 1, 2, 3, 4, 5, 6, 7 pieces, all of which have different shapes of trajectories I have to determine, plus I have to determine the times at which the arc changes. That's a lot of work. And as I said, it could take a lot of time to calculate. There's a paper, by the way, which gives you the complete solution and how do we work this out. So that brings me to the interesting part of the presentation. What do we do to get around this problem of inability to get real-time optimal solutions for problems of this type? And there are many other problems of this type. And one idea, and we don't want to sacrifice guarantees of safety. I still want all of my constraints that I showed you, the safety constraints for collisions and so on, and speeds, not to exceed speeds, to be guaranteed. How can I do that? One way to do it is using control barrier functions, which is a very general approach. Barrier functions have been around in optimization theory for decades, but it's only in the last 10 years or so that people started using them in dynamic optimization, particularly in optimal control problems. As they did so, people discovered that they're very useful, but a whole new research field emerges now because there's all sorts of interesting questions that you have to answer to make them practical. So this is just to remind you the big picture of bridging the gap between optimization and real-time control while guaranteeing safety. And if you want to adopt a model predictive control approach, MPC, you can do that, but even though it's easier to solve than an optimal control problem, you will get suboptimal performance. You will make linearization errors because MPC works in the nonlinear systems, but you have to sacrifice complexity. The models are still too simple. We'd like to get away from very simple linear models of vehicles, and they are still computationally expensive depending on, if you know anything about MPC, the receding horizon that you use. The more you want to look ahead and be predictive, the more expensive it gets. In the case of control barrier functions, they are really easy to solve, as I'll show you. You have a theoretical guarantee called forward invariance that if you start safe, you will stay safe throughout the execution of the trajectory. You can easily accommodate nonlinearities. You can have complex objectives, so that energy function that I showed you could be much more complicated than the quadratic. And you can also incorporate noise. It turns out to be pretty robust. But I still will have to sacrifice some performance, inevitably. And I may become conservative. And this is the big thing. How conservative do you want to get versus optimality? I can guarantee the safety of all vehicles in the road, and I can start a company selling the safest self-driving car in the world. One that drives no more than 5 miles an hour ever. I don't think I will go very far with such a company. That's been conservative, but certainly not optimal. So I want to push that. I want to start driving 50, 60, 70, 80, 100 miles an hour, but still guarantee safety. Which brings me to the theory of control barrier functions. So I will only take maybe 5 minutes to tell you the entire theory, but at least to give you the essence. So if you look at a generic optimization problem, you are in a certain search space or state space, and you would like to be able to reach a certain set of safe points, which is the intersection of the safe set. So you want to be able to stay in that green region. But you want to do that using a feedback control mechanism, something which gives you the power of feedback in your fingertips by having control laws that tell you how to do it in real time. And if I give you the specifications, meaning all the constraints and my objectives and so on, and maybe tell you a little bit more about the system and the environment, so that brings in elements of learning, then I would be able to close this loop and provide a control with a forward invariance property which says if you start out safe, I guarantee that you will stay safe forever. Forever within the context of my optimization problem. This is what CBFs bring into the table, or onto the table. How? Here's how. Let's consider this dynamic system which has very general dynamics, nonlinear as long as the Lipschitz continues. The only limitation is that I want my control to be linear, affine. So I want a nonlinear but affine and controlled dynamic system. Even that can be relaxed, as it turns out, but for now, let's stick to that. A control barrier function is really a continuously differentiable function of the state that describes a constraint that you want to satisfy at all times. For example, I don't want the speed to ever exceed a certain point, or I don't want the positions of two vehicles to ever become less than so much. It is what it is. You can do that. A control barrier function approach is one which maps this type of constraint into another constraint which brings in the control. See, the problem with this is it doesn't tell you what control you should be using to satisfy that. You have to solve the entire optimization problem to tell you that. A control barrier function constraint is one that looks like this. I'll explain the components. But the first thing to notice is that it gives you a u, which is linear. And what this basically says is that if you can solve this inequality, I will give you all of the controls that guarantee to satisfy this condition. The first two parts are just the so-called Lie derivatives. If you don't know what the Lie derivative is, it's just simply a derivative of any function. V here in general, here would be the V function, along the dynamics of a given system. So these are easily calculated. And then this is a choice that you make, and it's what we call a class K function. It's a strictly increasing function, which starts at 0. And the beauty of this approach is that if you can find all the controls that satisfy this inequality, you guarantee that. You guarantee it. So it's a sufficient condition. That's where conservativeness comes in. I guarantee that if you choose any control that satisfies this, you're okay. Safety guaranteed. Yeah, but if you pick a control which is super conservative, it won't buy you very much. So this is where it comes in. How do you modulate this conservativeness? This is how. This is by choosing the right type of class K function. So this opens up a whole new area of how do I pick the right type of class K functions to satisfy such inequalities with minimum conservativeness. Okay? So rewriting this constraint, I emphasizing that this is linear in U. Big, very important fact, because it turns out that you can solve now entire optimal control problems as quadratic programs over time. So as I said, this inequality provides a rule for you to choose the U that will guarantee to satisfy all of these constraints expressed as B sub k, B1, B2, and so on, and keep them forward invariant. So details, proofs, and so on. We just finished writing this book just a few months ago, so if you're interested, you can go find and read about the whole development of this theory. Now, you can also incorporate soft constraints, not hard safety constraints, but softer constraints. For example, in the case of vehicles, I would like to drive pretty much at this speed, but hey, if I go a little bit more or a little bit below, it's not the end of the world. And I'll penalize myself by delta. This should be a 0, but if it's not 0, it's not the end of the world. And so you can incorporate that. Now, how do you solve an optimization problem? Well, if you formulate an optimization problem of this general type, where this is quadratic now, and this is the delta that I'm using, it's an artificial relaxation variable. I'd like to keep it small to make this constraint satisfied as much as possible, but I'm not, anal about it. It's okay if I violate every once in a while. Then you solve this problem subject to very general state dynamics, the CBF constraints that replace the BK. So in my original problem, I've replaced all the BK of x less than or equal to 0 by these inequalities, which are linear in U. They tell me what control I need to use here to guarantee the original constraint, but they may be a little conservative. Same thing with CLF constraints, plus whatever decision variable constraints you have, which you have to also honor. So these are, roughly speaking, hard safety constraints, and these are soft constraints, which have replaced now the real original constraints, like I want to keep a distance between two vehicles also greater than so much. You have replaced it by something which is its associated CBF constraint, the underlying function that specifying the distance is this. But now you have introduced these derivatives plus the information through f and g of this, and these guarantee that you're safe. Now, you discretize time, and all you have to do now is solve a sequence of quadratic programs in u and delta, subject to the vehicle dynamics, the CBF constraints, the CLF constraints. Why is this a quadratic program? Because we choose quadratic objective functions. Granted, if you don't like that, then we will have a convex problem, not a quadratic, but a convex problem. But this is the most important thing. It's linear in the decision variables, the controls. And the safety constraints are guaranteed. It's easy to solve. Now we're really talking about, fractions of a second, by discretizing time and solving this quadratic program over time. So this is the theory of CBFs in a nutshell. Now, what are the issues? Each one of which could generate, books, papers, PhD theses, and so on, and some have been already written. Number one, what if the control in this inequality doesn't show up? Why? Because this quantity happens to be zero. The whole theory fails, right? The whole point was to come up with a rule, a formula, that tells me what u I need to satisfy a constraint like b greater or less than or equal to 0 that I want. Well, if this term is 0, I'm sunk. So either I have to make an assumption or I have to work around it. The answer is you work around it. You're not going to compromise on that because that's too important. Number two, is each one of these QP problems through discretization always feasible? That's a big problem. Turns out it's not. Because you discretize it. How? Who's to pick the delta? If you don't make a good choice, you may be infeasible. Number three, since the CBF constraint is only a sufficient condition for the original problems, how conservative are these controls that come from this nice inequality? So you need to measure this conservativeness and say, I'm not satisfied with that. I have to be a bit more aggressive. So there, you need to worry about that. What if the environment or the system is time varying? I need to extend this to time varying CBFs. What if the dynamics are unknown? So if I'm driving my own vehicle, maybe I know my dynamics. But the whole problem that I formulated for you assumes that I also know the dynamics of the other vehicles. Well, I might not. So I need to deal with that. All of these can be dealt with different levels of severity, but they can be dealt with, and I'm not going to go through it, but I will highlight how we solve them, some of these issues. Issue one, the idea of not having this show up can be easily resolved by keep on taking derivatives of this function until u shows up. You can always do that. This is a known trick from the calculus of variations, for example. If you do that, then you extend your definition of these functions, the C control barrier functions, from what we had before, we'll give it a index of 0, to a whole sequence until the number of times that you need to differentiate before u shows up. This can be 3 or 4, it's not going to be 100. But once you do that, then you create a slightly more complicated type of inequality constraint, from which again, linearly you will get u. But now you may have to take several derivatives, and this is a term that sort of encompasses all the lower level derivatives that you've taken, so it can be done. The feasibility. So this is where event-driven techniques save the day. The problem with the time-driven approach, as I mentioned, is that I have to pick the right delta. If I pick the delta too large, I'll be very suboptimal because over a period of time, the real solution may not be a constant control. Here I'm keeping it constant. So if I keep the time interval too large, I'll start degrading my performance. If I make it too small, computational complexity will kill me. But if I use event-driven techniques, in other words, I only resolve the problem only when I need to, trigger the solution with appropriate events, then you resolve this problem almost completely. There are a few exceptions. By the way, there's a side benefit. The unpredictability of event-driven control updating. If you execute your control this way, this is a general principle, you're predictable. If there's a malicious opponent that tries to screw you up by going in there and jamming you or simply stealing some information or whatever, you're too predictable. But if you update, you make the decision to resolve this problem on an event-driven basis based on whatever happens in the real world that you observe, even you don't know when the next time to update is. You just wait until something is happening. So you become unpredictable, hence more secure. But that's a parenthesis. On the time-varying side, what we do is we develop adaptive CBFs. The key idea is to choose the thing that you can manipulate, which are the class K functions, in ways that are typically parameterized. So for example, by choosing polynomials with some scaling factor, by adjusting these polynomials, you can adjust the conservativeness. That's the key idea, to adjust the conservativeness and also adapt. And this is where some learning comes into play. Fairly elementary learning techniques. There's another paper where we've done that for unknown dynamics. You can do that. Okay, and finally, if you have unknown dynamics, as I mentioned, I'm not going to get into details, but I will mention that there's a procedure that you can follow. You postulate a model which is general but affine in control. That's the one compromise that you make, just to be sure. And then essentially you adapt these functions, which denote the control model, but at each iteration, using whatever model you have postulated, you express the constraints that you need, and then you follow what I just described based on the postulated model. But at the critical step, you determine certain events. As I said before, the event-driven approach is essential to this technique, to solve the QPs, and this is the important theoretical contribution, you guarantee that even though now the times between solutions of these QPs are unknown, because they're event-driven, you guarantee that these original constraints are always satisfied. So you're always feasible, no problem. So that's the general idea of how you can deal with unknown dynamics, which is something that can happen a lot, not just in self-driving cars. So, in a nutshell, to bridge the gap between optimal control and the CBF approach, we design controllers, we call them OCBF, for optimal control with control barrier functions, in which what you do is you first solve the unconstrained problem, which is easy. Or, if you can afford a little bit more computational time, you throw in a few more constraints. You do the best you can with the time you have. Let's say 10 milliseconds. What solution can I get in 10 milliseconds? Once I have that, I inform my controller of what the constraints are, which I ignored here, let's say. And the controller, using the techniques that I described with all of the CBF constraints, can handle nonlinear dynamics, nonlinear constraints, complex objective functions, which could be also nonlinear, and noise, in order to deliver essentially an optimal tracker of the unconstrained solution. So think of it this way. If you solve an optimization problem, the ideal, the lower or upper bound, is the solution of the unconstrained problem. Right? That's the best you can do. Then you say, let me get as close to the solution as I can once these constraints start getting active. But I don't use the original constraints, as I explained. I use the control barrier function constraints, which guarantee the original constraints, but may be conservative. That's the price to pay. But then all I do is I try to track that optimal control. So this picture depicts what I just said. Find a solution in this problem, where this is an infeasible area, let's say an obstacle, and you ignore it. So this is the best you would do, could do, if this wasn't there. Then you try to come up with this blue curve, which is optimally tracking the red curve as best it can. The way you do it is first you determine the unconstrained solution, which becomes a reference signal. You might use some real-time feedback to come up with the reference control that you want, which in the simplest possible case might be the original one. But then this is the important thing. When you solve this optimization problem, trying to stick as close as possible to this curve, your constraints are these CBFs, which are guaranteed to satisfy the original constraints. So, in the simplest possible case, as I said, you don't even use feedback. You just say, I just found this red curve, just let's go with it. I'll just track it as best I can, but I'm going to guarantee that I'm tracking everything safely. So see here, I avoid the obstacle for sure. So this is this approach. So if you use this approach, you go through a process in which first you solve the same optimal control problem as I showed you before. So there's nothing new here. And you came up with some U star and X star, optimal control, optimal trajectory, as best you could. Then you observe the actual system, which may behave in a very nonlinear manner and have noise. So that's nice because feedback will compensate for noise. And then you come up with a reference signal. You come up with a nice function of the unconstrained, let's say, solution any way you want, or in the simplest case, ignore it and set U ref equals to U star. But these are examples, these are known in control theory, standard formulas in which you can create reference signals as functions of a desired trajectory, say, using feedback. Okay? So these are fairly standard, don't worry about it. And in the simplest case, just ignore everything and just say, I don't want to bother, I want to track the unconstrained solution. And then you have this formulation, which yes, looks a little difficult to follow, but note that you have nonlinear dynamics with noise, and these equations over here are the CBF constraints that have replaced your original constraints, but again, they're not difficult to calculate. These are fairly simple calculations. And you solve this problem by discretizing, as I said before. You can do it in a time-driven way or an event-driven way, but that's the recipe in order to come up with something which is guaranteed to satisfy the constraints. It's as optimal as it can be by trying to track the unconstrained optimum, and it guarantees safety. Let's see how that works for the merging problem, finally. Okay. So in the merging problem, I want to show you how we solve this problem for a merging problem, which actually is in Boston. This is the Massachusetts Turnpike, and this is a merging point. It's actually got a curve, so it's a slightly more complicated problem because I now have to include some comfort levels for turning. But this is something that I actually take pretty much every day myself. I come from here and I join the Mass Pike going west to go home. So this is on the left the way that a simulation, a reasonable simulation, would represent how the behavior of this merging area behaves. And this is what happens when you apply a solution based on what I described, with one assumption that everything is a cab, which I'll relax in 2 minutes. But for now, everything is a cab, so everything can communicate. And in fact, we also allow for the comfort. So if I run this and this, just for the eye test, you will see that this creates some queuing very quickly. Why? Because the rule is that the slower cars coming from the curve typically stop to let the fast-moving cars in a highway to get through, unless you find, like here, an opportunity to go through, and a bunch of them go through. But they have to stop. In contrast, here, nobody ever stops. And the thing to notice, which I have experienced in real life, is that sometimes you get a backlog which goes all the way back to the entry point. And I've seen this just a few nights ago. As a matter of fact, I was here facing, slowed down. I had to stop completely because this queue backed up like you see here. This never happens here. If you look carefully here, you will see that some of these dots decelerate or accelerate judiciously to, here, this guy decelerated a little bit to let the blue guy in and so on. So you can see how this works. All right. So one more thing. Just show you some numbers to give you a numerical sense of the benefits that you can get in terms of time, energy by itself, and then the total thing. And here we compare the actual optimal control solution, because we can solve this problem analytically, as I said. So this row with the OCBF. This parameter gives you a weight as to how much do you care about time versus energy. Right? So just here, get a glimpse of that. The real optimal solution is this, and the OCBF can get you very close. And this is with noise. So you lose a little bit of performance because of noise. So just to make a sense of what's happening. But what if not everybody is a smart car? What if, for example, this is a smart car and this is not a smart car, it's what we call an HDV, a human-driven vehicle. Then the car, the thinking car, says to itself, as I come to this merging point, I know that it's better for me to get ahead of this. But can I trust that this guy will let me go through? If it's an automated vehicle, of course you can, because it's been negotiated, agreed upon, the beauty of automation. The ugliness of having humans involved in the process is that if this guy had a fight with his spouse this morning, may take it out on him and say, no, I'm not going to let you go. How do you deal with that? So we have to start developing a theory for dealing with humans, and this is not, by the way, just in driving, but in everything in which you have machines and humans interfacing and interacting. In the case of transportation systems, which is what we're talking about here, clearly there are benefits from connected and automated vehicles. Enhanced safety, reduced congestion, reduced energy consumption. But if we start allowing HDVs, and it depends on what the fraction of HDVs is versus cabs, obviously, what can we do? Well, I've thought about this problem over the last 2-3 years, and so has Andreas and others, and I've come up with 3 general ways in which you can solve this problem. And clearly, the solution lies somehow in the intersection of these 3 ways. The first way is this. Go all out on developing good perception methods, computer vision and so on, and learn better HDV models. Try to predict how humans behave. And in real time, try to see how this human driver has driven his vehicle for the last couple of seconds and predict what's going to happen in the next couple of seconds. Okay, so that requires better estimation and learning. Prioritize safety and then optimize. So try to come up with methods, controllers, which guarantee safety at the expense of some optimality. But when I say guarantee safety, it's literally make the actions independent of what the HDV does. You kind of eliminate the risk created by the HDV. You paint him into a corner, you kind of push him out of the way, and you say, that's the way to do it. The third way is to use more economic mechanisms. I've been working on something that I call cooperation compliance, trying to come up with smooth, non-intrusive, transparent ways where you can get the human drivers to behave like you would like them to, and like they should, if you believe in social optimality. I'm going to spend the next maybe 5 or 10 minutes that I have left talking to you about this, because that's where we've focused our attention for the last couple of years, and we have a few results that I want to share with you, only at a very high level. I just want to get across the intuition. So let's take this interesting case, which is not a merging scenario, but sort of. It's a case in a highway in which you have a calf here, and an HDV here, right? And let's say that somehow we've decided that this calf is going to merge. He's going to do it unless he decides it's dangerous and he won't do it. And so the first thing that you realize is that he has a choice. He can choose to squeeze in here, or he can choose to go ahead of calf 1. So there's a binary decision to be made. Now, if I go with each one of these decisions and I solve an optimal control problem and the corresponding cost, assuming that this is the solution that this guy will follow, or that this is the solution, if I do that, which I should be able to do because I've shown you that we have a theory to do it and a set of practical ways to do it, then I can compare the costs, see which one is less, and choose the better one. Now, one important observation. In case 2, HDV behavior is irrelevant. You've basically boxed this guy out of the merging equation. You said, whatever you do, I don't care. Now, intuitively, you see if you choose this solution, it may happen that this guy speeds up a bit, this guy slows down. If this guy slows down, he's going to force this guy to slow down. So he's going to hurt the HDV, who is probably going to be pretty unhappy. But hey, from a social standpoint, the problem we solve is one in which we try to optimize the comfort. Well, I don't know about the comfort of this guy because he's not part of the equation there, but energy and time. So if at the end of the maneuver I've minimized the time and I've done it in a way which makes the human irrelevant, I should be happy. But of course that depends on whether method 2, case 2 or case 1 is better. So if you solve this problem, and it takes a while, you come up with this result. So the result here shows you the cost as a function of distance between the human-driven vehicle and the vehicle ahead of it, this distance, right? So intuitively, if this distance is big, again, I don't care about the human-driven vehicle. There's so much space, I'll just accelerate, get ahead of him, and he doesn't care, all right? But if the distance is small, that's trickier, because in order for that maneuver to be executed, this guy's going to speed up. Hopefully this guy will not speed up too much, and this guy will try to get in. So what it turns out is, first of all, the cost of the merge ahead of the HDV solution is fixed, because it doesn't really require any dependence on this factor. But the cost with the merge ahead of CAV1 problem is monotonically increasing. Conclusion, there's a threshold, there's an optimal threshold at which this cost exceeds this cost. So if the cost of this policy is less, you go with that, you merge ahead of 1. When the distance becomes large enough, given by this threshold, then you merge ahead of the HDV. There are a few assumptions that you have to make about the HDV in the sense that he's not suicidal. That's basically what it comes down to. We don't make any other assumptions. So he's not suicidal, he's not trying to kill you and himself, but as long as you make these reasonable assumptions, it turns out that this is the optimal solution. And that's nice, because it shows that here I don't have to care at all about the HDV. And here I do care a little bit, but when the distance is large, I really don't care. He's way too far behind for me to worry about. This idea, so this is the conclusion. There exists an optimal threshold on the distance, which is measurable, so that determines the optimal choice. Now the same principle, turns out, can be applied to the merging problem. Because again, merging problem is a little bit like merging, except that it's more dynamic, right? Cars move back and forth and so on, and there is a very fixed point which constrains me. See, on the highway, the merging point is a decision variable. I don't care exactly where I will merge as long as I do merge. But here I have to merge or else somebody dies. So the approach that we took is, suppose that we determine what we call a safe sequence for every cab. What is a safe sequence? Essentially what I told you before. Always merge ahead of another cab. Don't avoid merging ahead of an HDV, because that might work, but it entails some risk. So for example, 4 may have to merge ahead of 5, because 5 is an HDV. And the way that things look, it might. Well, don't allow that. One way might be to cooperate with 3, so that you speed up to the extent you can, 3 slows down, and you merge ahead of 3. Same idea as before. Or, if it turns out that this distance is much shorter than this distance, in other words, you'll get there way before this guy, that's pretty safe too. That's what we did. The results were surprising. Why? Because you expect that by introducing safe sequence, you're being conservative. You're sacrificing optimality. And so I would expect the curves that I show you not to be so cleanly separated, one better than the other. Moreover, this is compared, by the way, to the natural and most common way of merging, which is what we call the shortest distance first, which I think is reasonable to assume is what we do. You see somebody coming, and if you're closer, you say, I'll go first. And you also check speeds, but that's basically what you do. So let me explain. These are 3 different metrics. So this is travel time. And the grouping is in terms of traffic intensity. So let's take this case where the traffic intensity was 600 vehicles per minute or something like that. The blue is what you would expect is the now case. The case of human-driven vehicles, which apply the common shortest distance first approach. And this is the penetration rate. So this is where we are today, let's say. There are no smart cars. And then the penetration rate increases. You would expect that by the time you get here, anything that has to do with calves would pay off. This shows you that no, it starts paying off right away, and significantly. And this is with a smaller traffic intensity, so the gap is smaller, but still, it's like that. And the same is true for all the other metrics. Fuel consumption, energy, this is the real fuel consumption measured in terms of more realistic measurements. So once you get surprising results like this, one of two things is true. The student who generated those results screwed up. Okay? So you go back and you say, are you sure? Let's check it. Or you find an interpretation. And there is an interpretation. I don't think I have it because I'm running out of time. I need a diagram to explain it, to give you an interpretation. There's a paper which we will present in an upcoming conference where we talk about that. But let me try to explain to you, sort of roughly speaking. The real reason is this. If you merge like you do now, like I showed you in the example with the Massachusetts Turnpike merging, cars will stop. Inevitably, sooner or later, you have to stop. Once you stop, you have to restart and reaccelerate. That takes time and energy. That happens. With the approach of safety, that is eliminated. So even though you may lose some optimality in some cars when there's not high congestion, that's why when the traffic intensity is low, you don't see much difference. But when the traffic intensity is reasonably high, you see the difference. Even though you are conservative, the level of conservativeness is outweighed by the differential in performance. The savings that you get by not stopping ever outweighs the fact that you, on the average now, over all cars of course, you behave a little conservatively. Also remember, this is averages over all cars. It's social optimality. Some cars will not benefit from this safe approach because I am forcing, like the HDV that has to decelerate, I'm forcing that HDV to slow down. True. But then so many other vehicles or agents or players in this game or users in the system, they benefit so much that it pays off. So I want to just close with a few open questions, high-level open questions. The first one is the one that you just saw. What fraction of calves does it take to realize the benefits? The penetration rate. And this particular result shows you that at least in this case, at all penetration rates, you can benefit, even from one calf. The other question is how to bring in other players in the transportation game, bicycles, pedestrians, and so on, into the picture. That's a difficult question because they have different dynamics. All of them involve humans. I can't deal with a pedestrian the same way that I might be able to deal with an HDV. So we have to deal with them. How do we incentivize compliance for social optimality? I hinted at that. I think it's the third general approach you can take to get humans to play the game the right way and be socially responsible and create what we call sustainability. Then, this is sort of a side result. No matter what we do, at least in my practical experience, we get to be very smart. We get to apply these very sophisticated controls, but the benefits are still not like 300%. They are 5%, 10%, 40%, I think was what we were, 20 to 40% we were targeting in our RPI project. Okay, that's good, but it's not spectacular. Why is that? Because sooner or later, the transportation system has a capacity. If you're operating too close to the capacity of any resource system, there's nothing you can do. What are you going to do? There's nothing you can do. I mean, if I want more people to come into this room, I don't have a control mechanism to have them sit. There's so many seats. So what control can I have? Have you shuffle around and share the seats? No. What can I do? Have fewer cars on the road. And that brings us into shared mobility on demand. And the last thing I want to mention is, what's the role of learning? in all of these techniques, like learning optimal trajectories. I don't have time to go into that. We have tried that, and we're trying to be as learning incentivized as anybody else in improving our research results. So far, I must say, we have not found any spectacular learning benefits of learning techniques. We get, using sophisticated neural networks to learn the optimal trajectories, we get very comparable performances. But if you set your sights a little bit lower, there are holes in the design of these control trajectories which require a parameter here, a parameter there, which you can learn. So if you use learning judiciously, you can actually benefit from the learning experience, but not necessarily in sort of like a blind way. Oh yeah, let's learn everything. Let's give up everything that we knew about models and so on. So cars, we know enough. We can model them fairly accurately. Other processes in nature, we may not, and learning has more of a role there. So I think that I'll stop here, and I hope I gave you a good glimpse of how you can bring in a new theory, that of control barrier functions, into optimization. And that turns out to be, I think, an instrumental way to also making autonomous vehicles a reality. Thank you.
Great talk. Any questions for our speaker? Yes, Oliver.
Yes. So do you think that, this transportation automation, is this a control problem or is this an architecture problem?
Both, clearly. Both. The architecture problem is at a different time scale. The infrastructure, I think that's what you're referring to, perhaps. The infrastructure, the architecture of the system, but also it could be the architecture. Do you mean the architecture of the controller, of the control system? What do you mean by architecture?
Architecture, for example, so here you are trying to optimize the trajectory of a vehicle, one vehicle, right? So, and on one slide you did mention the cooperation mechanism design. So here, when you are trying to minimize the travel time and the energy, this is for this one vehicle. So related to that, so is this optimized trajectory for this one vehicle to follow, how does that mean for a group of vehicles? So if every vehicle is following your control strategy, and in the end, do they together actually end up with the minimum joint?
Yeah, I'm not doing that for one vehicle. I'm doing for everybody. That's why it's important to realize that what we're doing is a decentralized control. The problem has been decentralized, so every vehicle satisfies or obeys a particular design, but the actions that this vehicle take are intended to minimize the entire control zone, in my case the control zone. So if there's 50 vehicles in this control zone and a new one comes in and needs to design a trajectory, its goal is to minimize the travel time and the energy of everybody. But because it doesn't have to exchange information with everybody, it turns out to be a decentralized control. It only needs information from the vehicle ahead of it and the vehicle with which it may collide. So it's not selfish. What you would describe is what I call the selfish way. No, it is socially optimal, where the society is the group of vehicles, users in the system at the particular time.
So you're optimizing the control protocol, not the action of the individual vehicle.
By protocol, I think you mean what, as a
rules,
control
like
guy, I
everyone
would
is
call the
following.
control law or the control policy. Yes, but obviously, in order to execute this policy, I'm also optimizing the action at any time. But to benefit everybody. Benefit everybody. The original problem is a problem over all the users in a particular system at a particular time. And the actions taken are by one user, taking into account everybody else, but it turns out that it doesn't have to worry about everybody. Right? It only has to worry about those people that it can be affected or affect.
Thank you.
There's another question.
Oh yeah, I asked a similar question. Since
Okay.
the decision is made locally in
Okay.
each vehicle.
No, yeah, it is, but it's because it is a decentralized solution. If I had another original slide, I would give you the original problem, which is go to this merging area, and for every car, solve the problem of sequencing, which is a scheduling problem, and also the motion control, so that everybody benefits. But I skipped that because it turns out that you can decentralize the problem in this particular way.
So if you have all these vehicles communicating with each other, does it mean that Elon Musk is going to control the world?
Yes, I'm afraid there is that danger there, yes, which is why we have to worry about the mix of cabs and HDVs, allow humans in there.
You'll have different types of cabs.
You'll have different calculators. This is another problem. So you need standardization. This is one of the big problems. There is another way to deal with that, which is instead of communicating information across agents, you sense each other through your local sensors. The original Google car that was roaming around in San Francisco and so on was full of sensors. It didn't need to communicate with anybody else. It could sense what the other cars are doing. That's fine, but it's incredibly expensive, and also there are practical obstacles. Like, you know, if there's a tree between me and the other car, I can communicate, but I can't see it.
The traffic code.
There are trade-offs there. But you're right. Communication makes you vulnerable to what we all experience, security threats, you know, and so on. So it's an open field. Actually, an interesting question is, can you use control barrier functions to guarantee security, to set, to define, to formulate constraints that are specific to security, and say, what should I be doing to guarantee that those security concerns are never violated? We're looking into that. There is hope, but the argument is, how do you formulate what a security threat is? It's a little tricky. You have to know the attack that you're worried about.
Thank you for this interesting talk. I may have a question related to a control barrier function. So in this presentation, do you present how to design the control barrier function for continuous time domain? So I'm wondering, is there any way to get the similar result for discrete time domain?
Yes. So this is a modeling choice that you have to make early on. Right? So you want to model your system in discrete time or in continuous time. If you model it in discrete time, every set applies. I model it in continuous time because I live in a world in which I see the clock continuously. So my philosophy of many is let's stick to the continuous time model until I have discrete time, which is typically when I have to put my controller to the computer and the computer doesn't understand continuous time.
Yes, because I choose discrete time domain. So I calculate everything.
That's fine.
That's so I'm questioning if we design the control barrier function for discrete time domain, can we get the same result like 100%?
Yes, but it will be more vulnerable to the feasibility problem because you have to choose your time step. In that case, you would have to alter your discrete time model to be discrete time, but choose event-driven times at which you update your controller to bypass the feasibility problem.
Can I have another question?
Yes, please.
In the presentation, I think you consider the mixed traffic as well. So I'm wondering if there's any way to consider the driven vehicles and the stable in the model, and then we design the control barrier function that yeah.
Yeah, that's one approach. That's exactly my starting point for what I did. I said, let's at least be robust. But then I realized you can be more than robust. You can literally be independent.
Yes, because I feel that if we want to consider 100% safety in mixed traffic, we need to care about the personal control items of the vehicles. So can we do something like?
Actually, we're doing that right now, and the results are promising. So in that case, what we do is we actually have a simulation in which the human-driven vehicle is driven by a human. So in the simulation, the student designed that. That's what I was asking about. We don't have a joystick yet. She was pressing buttons, right, left, and so on. And She was driving as crazy as a human could, and we had another cab with control barrier functions, which would, discrete time, see what the driver is doing and guarantee by taking evasive action that they would never be a collision. So this is very work, but along the lines of what you say, essentially, you want to be robust about how crazy the driver is. So it looks like you can do it, but I don't know how conservative. From what I saw in the early results, it looks like the cab was being a little bit too conservative for my taste. So then you have to do some of these refined adaptive CBFs, things like that, which achieve a smaller margin between conservativeness and optimality. But yeah, but the choice of discrete time is something that you have to decide when you early on or it's the last.
Unfortunately, we're out of time for the questions. Let's thank our speakers.